All right, let's talk about intermediate phases. And line compounds. So we've talked about line compounds. So I want you to recall intermediate phase in a three-phase system. And I'm going to recall it visually, and we're going to remember what the free energy composition diagram looked like in such a case. And it looked, let's say, an alpha phase. And the beta phase. We had some intermediate phase. And, right, so the common tangent sort of looked like this, with a tangency there, tangency there. Let's see. I'm just going to eyeball this, tangency there, let's say. All right, so this was your generic kind of three-phase situation. And I want to remind really just about this region here. This was, let's say, I didn't label its phase. Let's call this phase epsilon. Right? This region of composition was an epsilon solid solution. So there's a finite range over which you have a solid solution. That is, the epsilon phase has variable composition within a range. Okay. So now, suppose that instead of being a solid solution, the epsilon phase is very intolerant of deviations from stoichiometry. So for instance, let's say we have A 1 minus n Bn, but in this case, n is fixed. It doesn't vary in nature. So this is a little bit more like a molecule than a solution, right? If n is fixed, it's a little bit more like a molecule than a solution. How does that look on the free energy composition diagram? See, what colors did I use? I used blue, green, and maroon, I guess. So, all right, so here's blue, as before. Here's maroon, as before. But now let's say that here's n. That's that composition. And this solution model is going to look like this. Right. What I drew is something that's really narrow. So there's a minimum to this curve, the composition at which we find this material in nature. But as soon as we deviate from that composition a little to the right or a little to the left, we have to pay a huge energy cost. You imagine this curve collapsing into almost the shape of a pin. And so my common tangent construction is going to now be like this. So let's just call this solution model, solution in quotes, because it doesn't really appear as a solution in nature anymore, for epsilon phase. So the solution model becomes very narrowly shaped like a pin. All possible common tangents are going to converge at the same point. That point is x of b equals n, right? That's that one composition that we find in nature. So you see how that's a geometrical fact? As this thing gets narrower and narrower, all common tangents are going to cross at that one point, right? Instead of crossing at different points, giving you a finite range of composition, they're all going to cross at that one point. And what that means is I no longer need a solution model. I no longer need a solution model. Oh, I only need one point. Right, so I no longer need a solution model. All I need is that one point. That one point is a one free energy point at one composition. Okay, so here, I can't help myself. I got to draw the mouse face plot. So here's the point. If you have a very, very steep free energy composition curve like this, right? Very, very steep. All possible common tangents that you could draw are going to converge at one point because of that very steep curvature down there, right? So this kind of to me looks like a mouse, right? So it's a mouse face plot. But the point here is that these whiskers are all the common tangents kind of coming together at one point. So let's look at some examples here in nature. I could start with the magnesium nickel system. So we looked at this system before. I don't remember why and when, but we did. And so here's a phase diagram. It's got a number of different phases. It has a liquid phase at high temperature. Let me grab a highlighter. It's got a liquid phase at high temperature. And then how many other phases? We have magnesium, which is HCP. We have nickel, which is FCC. And then we've got two other phases, which appear as line compounds. We've got this magnesium 2 nickel phase, which is a line compound. And this magnesium nickel 2 phase, which is also known as a Laves compound. Lav is a structure type. And this line compound down here, it actually broadens. Can you see this develop some width here? So at high temperature, this Laves phase develops some width. It can be made as a solid solution with a very, very narrow range of solid solubility. But when you drop down to low temperature, both of these intermediate phases appear as line compounds. So that's an example. And you know, one of the hallmarks of a line compound and phase diagrams with line compounds is that you have very different structure types. So, right, so you can kind of see how these are not, you know, you don't reach this hexagonal magnesium 2 nickel phase just by individually substituting out atoms from the HCP magnesium phase. And they're really fundamentally different structures. So I grabbed some images here of the magnesium 2 nickel and this magnesium nickel 2 Laves phase. These Laves phases are of interest for people that study magnetism because they have these triangular sheets, which are interesting for spin liquids and spin ices. And then this FCC nickel. I even found a paper based on some phenomenology here in switchable mirrors based on nickel magnesium films. So, right. But this is the point I want to make here is that, you know, these are very distinct structures and they're only occurring at very distinct compositions. That's the hallmark of intermediate phase. That is a line compound. So how would you draw the free energy composition diagram for the magnesium nickel phase? It would be drawn like this. Magnesium nickel, actually a magnesium nickel system, right? So for instance, at some low temperature, we have here, this is going to be X nickel. So here we have HCP magnesium on the left-hand side, FCC nickel on the right-hand side. This is going to be a delta G, and here's 0. And I simply have here a value that represents the formation of magnesium 2 nickel. A value that represents the magnesium of magnesium nickel 2. And my taut rope construction, or my common tangent construction, ends up being just a series of straight lines. This is magnesium 2 nickel. This is magnesium nickel 2. And these vertical distances are related to formation free energies. My taut rope right. So instead of being like a taut rope, this is now like, well, right, it's just sort of a string held up between needles, right, needle points. There's no more curvature apparent. All right, so now let's talk about the size of these vertical segments. Let's talk about compound formation energy. And that's often written as delta form. Okay. So what is a compound formation energy? It is the free energy change for formation of 1 mole of compound from the elements in their reference states. So, for example, right, I might have 2 moles of magnesium in its alpha phase plus alpha, let's say HCP, plus a mole of nickel in its alpha FCC phase. And these can react to form magnesium to nickel, right? And there's going to be a free energy of formation for that reaction. So you can see I'm using this term reaction, and we're writing things a little bit more like molecular reactions, right? Even though this is an extended solid, it's an extended solid with fixed stoichiometry. Or here's another example. 2 aluminum in its alpha phase plus 3/2 oxygen gas, right? Delta forming alumina. And there are, you know, an infinity of examples. So, right, line compounds formed from the elements with a formation energy, delta G. Okay. There's a detail. This formation energy is per mole of compound. When we draw free energy composition diagrams, we assume 1 mole total of the components. So there's a normalization that you need to apply in order to use formation free energies, as you might find in databases, in order to use those data in free energy composition diagrams. So for example, we need normalization to use delta formation free energy on a free energy composition plot. Right, so using the example of magnesium to nickel, let's see, I'm going to redraw the free energy composition plot quickly. Okay, and what I want to measure here, I want to figure out, right, let's talk about what size that vertical distance should be. This is magnesium to nickel. That green arrow, this is the change of free energy when 1 mole of atoms form magnesium 2/3, nickel 1/3. I want to stop and make sure people recall that this was pretty much our definition of solution modeling. Right? We have a model for how the free energy changes when you combine a total fixed amount of atoms in different composition ratios. So for example, a point on this plot represents 1 mole of total atoms. In this case, let's say 2:1, magnesium to nickel. Right? So 2/3 of a mole of magnesium, 1/3 of a mole of nickel combined to form this magnesium 2 nickel 1 phase. But this is different than the formation energy, right? This measure is 1/3 times delta form magnesium to nickel. So it's simply, 1/3 because I have 1/3 the amount of atoms. So that is kind of a algebraically simple point, but it's a conceptual point that it's easy to mess up. It's easy to mess up when you're trying to do a free energy composition diagram, when you're trying to model a system, and you go to the textbook or you go to the databases and you look at formation energies of compounds. And the formation energies of compounds are listed per mole of compound, right? So if I go over here, again, there are lots of databases out there, but they're all going to list something like this: properties of selected compounds. So here's a carbide, boron 4 carbide. I know you can't read that, but you know it's listing, let's say, delta H's, S naughts, per mole of compound, not per mole of total atoms. So you have to apply that normalization in order to, if you need to draw such plots. All right, I want to give you some examples of line compounds in nature and in technology, and then we'll come back to discuss the thermodynamics a little more. Before I move on to some examples, are there questions about this algebra, this arithmetic, the concept of formation energy, the mouse face plot, anything of that nature? No, okay. Okay, so let's, I have some examples here. I should have animated this, I didn't. We can just walk through this one at a time. There's an infinity of examples of line compounds. So I just want to show you some of different types. So here's an example which speaks to the problem set, actually. I lost my highlighter. What happened there? Let me get my highlighter back. Okay, so here's the copper silicon system. So you can see that you can get a fair amount of silicon into copper, up to 10%. That's this kind of purple region. There are silicon bronzes and silicon brasses, that is bronze and brass alloyed with silicon. Those are ternary systems, but silicon tends to be a pretty useful additive for copper-based alloys. I used a silicon bronze when I was in grad school, and we were designing high pressure cells that needed to be actuated at low Kelvin, like below temperature, below 1 Kelvin. And below 1 Kelvin, you can't use lubricant. You can't just use WD-40 because it'll freeze. And so you have to look for metals that slide well against each other. And it turns out there's a whole family of silicon bronzes that various space agencies around the world have developed in the last century. Because space is another application where you have moving parts. Sometimes you have machinery that needs to move against each other. And you can't just have WD-40, right? There's no real lubricant that you can use. And so there are certain silicon-based bronzes that have been developed for that application. And I didn't know anything about all that really when I was in grad school, but I needed something that would work for my high pressure experiments. So we ended up with that. So let's see, there's a couple other solid solution phases. There's this little guy here and this little guy here. And then there's, of course, a big liquid phase. But how many line compounds are there? A trick question, somebody please. How many line compounds are there in this system?
Is it 3?
It's not 3. That's why it's a trick question. Somebody else?
4.
4. Yeah, I didn't see who that was. Right, thank you. It's 4. So there are the 3 here, which are intermediate phases, right? There's this really funny composition here, 0.08, 0.17. There's this thing, and there's this thing. And I don't know anything about these phases, but I do know that they're probably very distinct crystal structures with distinct properties, right? You can say that as an educated material scientist, not knowing any details, right? You can just say, oh, these must have different crystal structures. They must have different properties. Okay, so those are line compounds. They appear as lines here. But what about over here? Silicon. Silicon's not an intermediate phase, but it is a line compound. This solid silicon phase appears to have no equilibrium solubility of copper. Now, in reality, you always have some finite solubility of a solute in a solvent. You know this from maybe a month and a half ago. We did this on a problem set, something that's called there's always a solution. Because of the driving force of entropy, you can always get some solute into a solvent. However, in many cases, that solubility limit is very, very low. So in the case of silicon, the solubility of metals is very, very low. The solubility limit is typically parts per billion. So in principle, there is a purple region extending along this y-axis of solubility of copper into silicon. However, it's at the parts per billion level. So on this plot where you go from 0 to 100 atomic percent silicon, you don't see it. And that's true of line compounds in general. There's always some solubility, but it's often so narrow that you can model as if there's no solubility. That's not just an academic point. Doping semiconductors is why we're able to talk to each other over Zoom. Without doping, there is no semiconductor devices. There is no electronics revolution. So the fact that you can dope some metals into silicon is as important as it gets. And the solubility limits can be in the parts per billion. They can be sometimes in the parts per trillion, but they're rarely above parts per billion. Anyway, so on the last piece that you're going to do some problems around doping semiconductors. So I just, I do want to point that out. There's always a solution. Good. Okay. What about this one? This is gallium arsenic system. And so gallium arsenic system has a very famous line compound right up the middle, gallium arsenide. So why is gallium arsenide important? Does anyone know why gallium arsenide is important? Let's talk about technologies that are based on gallium arsenide. Does anybody know? All right, well, the two areas where you're going to find gallium arsenide are places where silicon either isn't fast enough for electronics, or you need to use light in addition to electronics. So where silicon isn't fast enough are the transmitters and receivers of your phones, right? Gigahertz RF networks. Silicon's not fast enough. So the transmitters and receivers of all modern telecommunication devices, including your phones, are based on what's called 3-5 semiconductors, such as gallium arsenide. Another place, so there, the transistors and diodes and so forth are just made out of a gallium arsenide wafer instead of out of a silicon wafer. Another place you're going to find it is anywhere you need light. And so gallium arsenide and alloys thereof, which we don't show here, are the basis for all optoelectronics and photonic technology. So right now we're zooming, but likely some part of the data between me and you is carried by fiber optic. And fiber optics are ways of transmitting a lot of information over long distances at low power by using light instead of electrons. And so at the point where the light and electrons are transduced, you have gallium arsenide and similar material-based chips doing the work. So that's an important and famous line compound. Here's another one. Right, here's another system where carbon and silicon each don't really dissolve in each other, right? You have these apparent line compounds along the y-axis, but there's another line compound right in the middle, silicon carbide. Silicon carbide is a refractory, some people will say it's a ceramic, some people say no because it doesn't contain oxygen. That's kind of a material. It's basically a refractory material. It's used for grinding. So it's of enormous industrial importance. It also is an emerging semiconductor material for high power electronics. And high power electronics is the idea that you could replace discrete, bulky power handling equipment with integrated power handling equipment. So I think these power substations that you see when you're driving by on the highway, these big they take up a whole property lot and they buzz at 60 hertz. Or these cans that you see hanging from the utility poles that down convert to a voltage for houses, right, 220 or 115. The idea that you could replace those discrete elements with integrated circuitry right? Saving power, saving money, saving weight, and so forth. That is the field of power electronics. And the thing is, you can't do it with silicon because silicon doesn't perform well at very, very high voltages. So you need new semiconductors that perform well at high voltages. Silicon carbide is one of the leading candidates. So in 50 years from now, if the idea of a power substation is like a thing of the past, it will be due to silicon carbide and similar high power electronics that are being developed today. Right. And this last one, this is a big old mess, right? This is the titanium sulfur system. This is a neat system because, first of all, it has like everything in it, right? It has eutectics, it has paratectics, it has a bunch of line compounds, it has line compounds that broaden into intermediate phases as you raise the temperature. It has sulfur, which is a liquid below 500 C, it melts at 220. And titanium, right, which doesn't melt till 1670. So it has this totally wacky kind of mismatch between two elements that are nothing alike. This system contains 2D materials. 2D materials are of a lot of interest today in semiconductor technology. Titanium sulfur system is the basis for the original lithium-ion batteries. About a third of the Nobel Prize work that was recognized recently in 2019 with the chemistry Nobel Prize was for work on titanium sulfide-based cathodes. Why? It's a layered material, so you can shove a lot of lithium in there. Anyway, there's a lot of good stories to tell in the titanium sulfur system. So these are, 4 examples, systems that have line compounds and other things. Before I move back to the board, do you have any questions on reading these, interpreting these, using these?
Yeah, I have a quick question. So on the bottom left one and the top right one, are those both, do they both contain 3 line compounds?
Yeah, so for example, let's look at the silicon carbon system. Carbon here is a line compound. Line element, I guess. It's not a compound. So a bit of a terminology there. It has 0 apparent solubility of silicon in carbon. Right? Silicon is a line element. Right? It has 0 apparent solubility of carbon in silicon. Again, there is some, but it would be invisible on this plot. And silicon carbide is a line compound. Right? So again, here's a line, here's another line, and here's another line. And it doesn't have to be that way, right? Here's a case of a line and an element that actually does have a pretty wide solid solution range, right? So it's not that all elements are always pure, right? That's definitely not the case. But the low temperature, what I could have a look here at the silicon carbon system at low temperature. At low temperature, actually similar to gallium arsenide at low temperature. It's going to be a really boring free energy composition diagram at low temperature. Let's draw it. Let's draw what that looks like. So would anyone like to take a stab at how I would draw a free energy composition diagram for the silicon carbon system at low temperature? Here's silicon, here's carbon, here's delta G, here's 0. And let's say this is 50-50. So first off, do I need any solution models? Right, I don't need solution models because nature has informed solutions. So no need to model solutions. So what do I need instead of solution models?
Just like the taut rope, like the lines.
Yeah, all I need is a number to represent the free energy change on forming silicon carbide. I just need that point, right? And similarly, carbon from carbon doesn't take energy to form. Silicon from silicon doesn't take energy to form. No solution models anywhere needed because nature has informed solutions. And here is my free energy composition diagram. It is just a triangle. So it's simplified. It's simplified a lot. Any other questions on the meaning or importance of this stuff? I'll go back to the slide quickly, and then if there are no more questions, I'll finish up on the board. So getting back to my trick question, I suppose that because silicon is not a compound, the right answer probably was that there are 3 line compounds, but there are 1, 2, 3, 4, you'd say pure phases in the system. And don't worry, I'm not going to try to ask trick questions on an exam or anything like that. But you know, the thermodynamics here is that this is a pure phase. This is a pure phase. This is a pure phase. This is a pure phase, meaning it's always going to be a known composition, never going to be alloy. This is a pure phase. Right? This is a pure phase, and this is a pure phase. They just appear as single points on the free energy composition diagram. That's what I meant to say. Okay, let me move back to the board. Just make a couple conceptual points, and we'll finish up. Comparing solutions at equilibrium to line compounds at equilibrium. So this is going to be two solutions. Let's imagine an alpha phase and a liquid phase at equilibrium. And I'm going to draw just a representative phase diagram, just to have something in mind. So here's alpha, here's liquid, here's X, here's temperature. And I'm going to imagine now, right, some equilibrium, alpha liquid equilibrium, right? As I drew one tie line there, right? Alpha liquid equilibrium. Just an example. This is no system in particular. We know that along that line, dg equals mu1 alpha minus mu1 liquid dn1 alpha plus mu2 alpha minus mu2 liquid dn2 alpha. This is just recalling previous stuff. We have internal composition variables. Right, the compositions are variable, right? Composition variables. So, you know, we have N1 alpha, we have N1 liquid, we have N2 alpha, we have N2 liquid. And if we have conservation of mass, and we can boil this down, let's say to X1 alpha and X1 liquid, right? So we have these composition variables. We're familiar with that. And the equilibrium condition dg equals 0 satisfied by common tangents. What do I mean? Coefficients equal to 0. That's what the common tangent ensures, that the coefficients are 0. Chemical potentials are the same in both phases, so that the coefficients are 0. Chemical potential is the same in both phases, so the coefficient is 0. That's ensured by the common tangent construction. So this is recalling, right? Now let's imagine two line compounds. I drew an unnecessarily complicated example. Let me just follow through on that. B3A2 and B4A3. How did I come up with that? Well, I sketched an imaginary phase diagram, and I had to follow through on my sketch. So I had, what did I have? I had like this, and then like this, and then like this, and then like this. And that means I had a congruent melter. I had this, and then I drew as this, and then like this, paratectic, and something like this. I had this complicated thing which I drew. And the point is not the complicated thing. It's really, I have some two-phase region down here at low temperature where I have two line compounds coexisting. So let's see. The Gibbs free energy of B3A2, right, 1 mole of that thing is 3 times the Gibbs free energy of B in its reference state, plus 2 times the Gibbs free energy of A in its reference state, plus delta G formation of B3A2. Right? The Gibbs free energy of B4A3 is 4 times that of pure G times 3 times that of pure A, plus the free energy of formation of B4A3. Okay. There are no internal composition variables. That's the key point. Before we had composition variables because the composition of the phases was variable. Now we don't have that. What that means is that the equilibrium condition dg equals 0 is satisfied trivially. There's no need to do common tangents. There's no need to equate the chemical potentials because there are no internal composition variables. The compositions aren't changing. Right. I can write out the total Gibbs free energy. It's going to be determined just by the phase fractions. Phase fraction of the 2,3 phase times, let's say, 1/5 of the Gibbs free energy of the 2,3 phase, plus phase fraction of the 3,4 phase, 4A3, times 1/7 of the Gibbs free energy of the 4,3 phase. And these phase fractions are determined by Leverage law. This is really the point. When you have line compounds in coexistence, in equilibrium, there are no internal composition variables. Whereas when you have solution phases in equilibrium, the internal compositions are variable. And that's what's led to, everything we've been enjoying over the last month and a half is the fact that in solution phases, the compositions are variable. And now we have these cases where the compositions are not variable anymore. Okay. I want to leave you with one final thought, which is leading into Wednesday's lecture, which is the case of metal oxides, which are line compounds. So, it's on topic, but I want to just introduce this and get this in your minds. Let's imagine reacting metal M with 1 mole of oxygen to form an oxide. Okay, so Zm plus O2 gas reacting to form MgO2. All right, what's Z? How do I determine Z? Anybody? Does anyone know some oxides? Name for me a common oxide that you know. What is rock? What's the main component of rock? What's the main component in window glass?
Silicon oxide?
Silicon oxide, okay. So for silicon, Z is 1. Yeah, easy. Does anyone happen to know an example of an oxide for which Z is not 1?
Magnesium oxide?
Yeah, magnesium oxide is 1 to 1, right? So in that case, Z would be 2. All right, good. Oxygen, always O2 minus, right? In compounds. So Z is determined by charge balance. Oxygen is always O2 minus. And metals have various oxidation states. Can't write it anymore. Metals have various oxidation states. That's what that's supposed to mean. Some metals have more than one oxidation state, right? So that's Z. Here, M is in its reference state. Right? That could be solid, liquid, or even gas. Although we don't really encounter that so often. But, you know, oxidation of metals at low temperature, the metals are solid unless it's gallium or mercury. Oxidation of metals at high temperature, a lot of them are molten, right? So this matters for high temperature electrochemistry. All right, oxygen always in gas phase. We're not talking about low temperature physics here, so oxygen is always going to be in its gas phase. And these oxides are line compounds. Right. That Z is not a variable. That Z is an integer or a rational fraction, and it's fixed. Right. SiO2, magnesium oxide, Al2O3, so forth. Right. Okay. So when we return on Wednesday, we're going to talk about the thermodynamics of this reaction. We're going to use this property of being line compounds, and we're going to use a bunch of other things as well.